Here is another example. Determine whether the given function is a permutation of R. Here, f from the reals into the reals defined by f of x equals x cubed over x squared plus 1 is our function. So we're going to determine whether this function is a bijection. We're going to determine whether this function is one-to-one and onto. As it turns out, this does happen to be, this f does happen to be a permutation of R. So let's just confirm it. So first, let's show that f is one-to-one. F is one-to-one. Let's confirm that. Now, this time we're not going to go with the standard procedure f of a, set f of a equals to f of b and determine whether a equals b. That's because if we do that, we will end up with a very complicated polynomial equation on a and b. Instead, let's use calculus to show that this function is monotone. When a function is monotone, it could be increasing, monotone increasing, or it could be monotone decreasing. In both cases, either case, the function will be one-to-one. So let's proceed. Let's find the first derivative of f. So f prime of x. Now observe that our function is a rational function. It has a numerator and a denominator, so we will use the quotient rule. If f equals u over b, its derivative f prime is a vu prime minus v prime u over v squared. So we're going to use the quotient formula in this case. So we need a v times u prime, in this case 3x squared, minus v prime, in this case 2x, times u, in this case x cubed, over the denominator square, v squared, in this case x squared plus 1 squared. Now, let's simplify. So when we distribute, we get 3x to the fourth, but then we're subtracting 2x to the fourth. The result, x to the fourth. Then plus 3x squared. From this result, we can see that the numerator is never negative. It's 0 or positive. 0 when x is 0, positive otherwise. The denominator is always positive. Consequently, this first derivative is greater than or equal to 0. That's sufficient to conclude that our function is monotone increasing, therefore one-to-one. So here f is one-to-one. Now let's show that this function f is also onto. Once again, we're not going to go the traditional direct way. The traditional direct way would be, let C be a real number, set f of x equals to C, and look for real solutions of that equation, f of x equals C. Why? Because it will become a complicated equation to solve. So instead, let's pay attention to the following features of f. So first, f is a continuous function. So here, f is continuous on the set of real numbers. Why? Well, it is a rational function. It will only be discontinuous whatever the denominator equals 0. Now here the denominator is never 0. If your values of x are real, x squared plus 1 is never going to be 0. So consequently, this function is continuous in the set of all real numbers because there are no real numbers where the denominator is 0. So here f is continuous on R. Also, if we take the limit, so also the limit as x approaches infinity of fx here is going to be infinity. Reason, we have a polynomial over a polynomial, and the polynomial in the numerator has higher degree than the polynomial in the denominator. So an application of L'Hopital's rule will reveal that the limit as x approaches infinity of f of x equals infinity. And finally, the limit as x approaches negative infinity of f of x will be negative infinity. Similar reasoning, the polynomial of the numerator has higher degree than the polynomial in the denominator. And the sign of this quotient will be negative because now as x approaches negative infinity, your numerator is negative, your denominator is positive, so your result is negative. So there you have it. This function has to be onto. It has to be onto because no matter if you visualize it, here's your x-axis, your y-axis. You pick any real number on the y-axis whatsoever. Since this function is continuous and it is approaching infinity as x approaches infinity, at some point there is going to be an intersection. So there is always a solution. Here is your fx, here is your c, so fx equals c always has some real solution. Now let's look at the actual graph of f of x equals x cubed over x squared plus 1 to confirm each of these remarks. So there is our equation and there is our graph. So it's monotone increasing, it's continuous. As x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity.